Hi everyone, I hope you're okay and I hope that the videos will keep uploading are helping you out. On this video guys, I'll be tackling the fifth question from the worksheet I've compiled, which has 8 questions in total, and all of these questions guys are focusing on chemical equilibrium, and secondly they are all extracted from past exam question papers. So please do take this seriously guys. I strongly believe that knowing how to tackle exam questions will give you an edge whenever you write your final examination. So please do share the video to your peers so that they may have the same edge as you. And please guys, help us grow the channel by just subscribing. Okay, a reversible gaseous reaction is allowed to reach equilibrium in a closed container at different temperatures and pressures. Ne? The graph below shows the percentage yield for this reaction at 30 kilopascals as the temperature increases. Okay, we have our reactants and we have our products. Ne? And I can see that as temperature increases, according to this graph, as temperature increases, the percentage yield will increase. And the percentage yield will only increase if the products increase. Are you together guys? And for us to increase products, that means the increase in temperature favors the forward reaction. Are you together? And I know that guys, by increasing temperature I will always favor the endothermic reaction. If my forward reaction is favored, that means the forward reaction is endothermic, and hence the change in enthalpy will just be a positive number. Are you together? Okay, they want us to state Le Chatelier's principle in words. It simply states that whenever a reaction at equilibrium in a closed container is disturbed by one of the factors affecting equilibrium, the system will shift in such a way that it will oppose the disturbance. Are you together? The system will shift in such a way that it will oppose the disturbance that was made. 6.1.2, we are told that the heat is positive. Yes, it is positive. We are supposed to use Le Chatelier's principle to explain this statement. Ne? As temperature guys increases, I can see that my percentage yield increases. So that means as temperature increases, the product increases. That will only happen, I can only increase my products if I favor my forward reaction. Are you together? So I can now conclude that an increase in temperature favors the forward reaction, and hence the forward reaction is endothermic, and that's why the change in enthalpy is positive. That's why the change in enthalpy is positive. No? Okay, and then now we are told that the graph below show the percentage yield for this reaction as pressure changes at constant temperature. The graph below show the percentage yield for this reaction as pressure changes at constant temperature. They want us to explain the effect of an increase in pressure in the equilibrium position of a reaction. Whenever guys you increase pressure, you will always favor the side with the least number of gases. Né? Over here we have reactants and we have products. Né? I can see that as pressure increases, the percentage yield also increases. And I know that my percentage yield will increase if products increase. Are you together? And for my products to increase, I need to favor the forward reaction. Are you together, guys? So over here, an increasing pressure over here, guys, I can see that it just shifts the equilibrium position towards the right. By shifting the equilibrium position towards the right, you are basically favoring the forward reaction. Are you together? So an increase in pressure will just shift the equilibrium position towards the right. And please note that guys, that will only happen if ever the product has the least number of gas moles compared to my reactants. That will always be true. Né? Okay, which one of the following represents the above equilibrium? Let's check the number of gases we have on the left hand side compared to the ones on the right hand side. And whenever guys we check the number of gases, we just focus on the stoichiometric coefficients. Excuse me. For reaction 1, on the left hand side we have 2 plus 3, that's 5 gases, and then we have 3 gases over there, and then we have 2 gases here and 3 over there. We have 2 and 2 over there. The only reaction that has the least number of gas moles on the product is reaction 1. So reaction 1 is the one that represents that's equilibrium reaction. For 6.2, we are told that a mixture of 0.2 moles of hydrogen chloride and 0.11 moles of oxygen gas is sealed in a 200 cubic centimeter flask at a certain temperature. The reaction reaches equilibrium according to the balanced equation. Okay. Then we are told that it is found that 1.82 grams of hydrogen chloride is present at equilibrium. Okay. So I simply have 4 hydrogen chlorides. I have oxygen. I have 2 chlorine, and then I have 2 moles of steam. This is my initial number of moles, the change in my number of moles, the equilibrium moles, and then this is the equilibrium concentration. Remember that, guys, for us to calculate the equilibrium constant, we need to have the concentration of the products as well as the concentration of reactants at equilibrium. Okay, we were given 0.2 moles of hydrogen chloride and then 0.11 moles of oxygen. And then we are told that the number of mole, the mass of hydrogen chloride at equilibrium is 1.825. So we can simply find the number of moles at equilibrium. That's basically 1.825 divided by the molar mass. For hydrogen chloride, hydrogen is 1. For chlorine, I have 35.5. So whenever I find my answer, I'll say 1.825 divided by 36.5. This will simply give me an answer for 0.05 moles. This will give me an answer for 0.05 moles. Are you together? So I now know that, okay, at equilibrium, I'll simply have 0.05 moles. That means I have used some of the moles of my hydrogen chloride. How much did I use? Initially, I had 0.2, but at equilibrium, I'm only left with 0.5, so I'll just find the difference between the two. It's 0.05, right? So the answer is just to 0.015. After finding the number of moles that I've used, I can simply find the number of moles of oxygen that I've used and the number of moles of chlorine that I've produced, as well as the number of moles of steam. Okay, I know that, guys, I know that I need to use 4 moles of chlorine with 1 mole of oxygen to form my products. But now I did not use 4 moles, but I only used 0.15 moles. 0.15 moles of hydrogen chloride. I want to know how much of oxygen will I need to use. That 0.15 is equal to 4x. Then x is basically 0.15 divided by 4. That's equal to 0.0375. That's 0.0375. Okay, and then now we can go find the number of moles of chlorine. I need to use 4 moles of hydrogen chloride to form 2 moles of my chlorine gas. But I only use 0.15 of hydrogen chloride. I want to know how many moles of chlorine did I use. I'll just cross multiply. 2 multiplied by 0.15 is just 0.3. 4 times x is just 4x. Then x is basically 0.3 divided by 4, which will just give me 0.075. Are you together? I'll also get 0.075 over here, guys, according to the ratios, because I can see that 4 is to 2. Same thing applies with steam, 4 is to 2. So the number of moles which are produced here are the same number of moles produced there. Initially, guys, I had 0 because the products were not formed when the reaction began. Yeah? Okay, and then now let's find the number of moles at equilibrium. For oxygen, I had 0.11 moles, but I've used 0.0375. I want to know how many moles do I have left. I'll be simply left with 0.0725. Are you together? And then for chlorine, I had 0 initially. At equilibrium, I have 0.075. That means I'm still left with 0.075. 0.075 over there. And then for my volume, the volume is 0.2 cubic decimeters. 0.2 cubic decimeters. I just need to divide the number of moles with 0.2. So 0.05 divided by 0.2, this will just give me 0.25 moles per cubic decimeter. 0.0725 divided by 0.2. This will just give me 0.3625. 0.075 divided by 2. I'll simply get 0.0375. 0.0375. So therefore the equilibrium constant Kc is the concentration of products. Our products, we had steam H2O squared and then Cl2 squared all over oxygen multiplied by hydrogen chloride to the power 4. Kc, guys, is just the ratio of the concentration of products to the concentration of reactants raised to their stoichiometric coefficients. So for my steam, I just have 0.0375 squared, 0.0375 squared for chlorine. And then for oxygen, I just have 0.3625. And then I have 0.25 all raised to the power 4. So the answer over there is just 0.0375 squared multiplied by 0.0375 squared all over 0.3625 multiplied by 0.25 all raised to the power 4. So my final answer, guys, is just 0.11. Let me check if I pressed my calculator correctly. Okay, I simply get 0.00139655572, and hence the Kc is just 0.0014. 0.0014. That's how, guys, we're supposed to deal with this question over there. So please do stay tuned and wait for more videos. Did I punch my calculator correctly? No, man. Did I? 0.075 divided by 0.2. Yo, nkosi yami. Okay, guys, before you go, let's fix this thing over there. I've pressed my calculator wrong there. So let's just change the concentration of our products. Is 0.375. Just say 375 over there as well. 375. And then that means our Kc will be different from what we got. Excuse me about that, né? So it's just 0.375 squared times another 0.375 squared over 0.3625 multiplied by 0.25 to the power 4. And then our answer is just 13.9655174. 13.97. This is our Kc value. That's how, guys, we could have dealt with this question over there. Excuse me about the mistake now. But that's how, guys, we're supposed to tackle this question. So please do stay tuned and wait for more videos. Thank you.